Hello everyone, myself Srasti Srivastava, and today we are going to discuss the topic Schmidt Orthogonalization process. Let V be an inner product space and let beta 1, beta 2 up to beta n be any independent vectors in V. Then one may construct orthogonal vectors alpha 1, alpha 2 up to alpha n in V such that for each k equals 1, 2 up to n, the set alpha 1, alpha 2 up to alpha k is a basis for a subspace spanned by beta 1, beta 2 up to beta k, or every finite dimensional inner product space has an orthogonal basis. Now moving on to its proof, let beta 1, beta 2 up to beta n be the basis of an inner product space V. The orthogonal basis alpha 1, alpha 2 up to alpha n is constructed in such a way that each alpha I where 1 is less than equal to I is less than equal to n will be expressed as a linear combination of beta 1, beta 2 up to beta n. Let alpha 1 equals beta 1, then alpha 1 cannot be equal to 0 as beta 1 is not equal to 0. So alpha 1 is linear combination of beta 1, which is equation number 1. Now taking alpha 2 equals beta 2, which is the vector projection of beta 2 on alpha 1. Now alpha 2 equals beta 2 minus beta 2 alpha 1 into alpha 1 upon norm of alpha 1 whole square. Now this is equation number 2. Here alpha 2 alpha 1 equals beta 2 alpha 1 minus beta 2 alpha 1 upon norm of alpha 1 whole square into alpha 1, which becomes 0. Hence alpha 2 is orthogonal to alpha 1 and alpha 2 cannot be equal to 0 because if alpha 2 equals 0, then from equation number 2, this is equation number 2. Now beta 2 equals beta 2 alpha 1 into alpha 1 upon norm of alpha 1 whole square equals beta 2 alpha 1 into beta 1 upon norm of alpha 1 whole square, which implies beta 1 and beta 2 are linearly dependent, which contradicts our supposition that beta 1, beta 2 up to beta n are linearly independent. That is, alpha 1, alpha 2 form orthogonal set. Now let alpha k equals beta k minus alpha 1 beta k into alpha 1 upon norm of alpha 1 whole square minus alpha 2 beta k into alpha 2 upon norm of alpha 2 whole square minus alpha k minus 1 beta k into alpha k minus 1 upon norm of alpha k minus 1 whole square. This is equation number 3. Now it can easily be said that alpha k is orthogonal to any vector of the set alpha 1, alpha 2 up to alpha k minus 1, which implies alpha 1, alpha 2 up to alpha k is orthogonal and alpha k is not equal to 0. Otherwise, as in equation number 2, beta 1, beta 2 up to beta k are linearly dependent, which is contradiction. That is, alpha k is not equal to 0. So by extending the process up to nth vector, we can construct an orthogonal basis alpha 1, alpha 2 up to alpha n with the help of the given basis, that is beta 1, beta 2 up to beta n. The process of construction of the basis is known as Schmidt Orthogonalization process.